In this experiment, you're going to calculate the speed of sound and determine its percent error or experimental error in your observations and results. First of all, you need to get a tuning fork. And so this is our tuning fork. And what I need you to do is you're going to find it. This one on it, it's got a number written on there, and it tells me that this is the note C 256 hertz. So record that in a data table. Your second thing is you're going to get a tube. It's a plastic tube. It's open at both ends. Okay, but we're going to close one of the ends. But it's a cylinder and it's got the same volume all the way down. So next thing we're going to do, take out your meter stick and record its internal diameter. If you're going to be really good, get the inside, not from the outside. So now you're going to get that. I'm not going to give it away, but it goes, 2.5 roughly, 2.5 centimeters. Okay, so I've got the diameter, and I've got my frequency. We also need a little mallet here to get our tuning fork working. Hopefully you can hear that. All right. So that is vibrating at 256 hertz, 256 vibration cycles every second. So it's quite impressive. Okay. The next thing that we're going to do is we're going to get a big graduated cylinder or some kind of cylinder that we can put water in. And then what we're going to do is we're going to put our tube inside the other. So I need something with a bigger diameter than this. So I'll go get that and I'll be right back. I recommend that you work in pairs or even a group of 3, but I want each person in the group to try each job so they get used to going on for each part. So I've got a big graduated cylinder here, and I filled it about 2/3 to 3/4 full of water. Don't go too much in there. Okay, so I'm going to take my open cylinder and put it in. So now what I have with this cylinder, this one, is I have an open top still, but the bottom is closed off by the water. And because it's in this container of water, I can actually change the length before it hits the tube. So right now, this tube, just so you can see it, so I'm squeezing it against the side. And what I'm going to do is I'm going to measure from the surface of the water to the top of the tube. So right now I'm at about 32.5 centimeters length in that tube. But if I go down a little further, now I can measure from the surface of the water to the top, and I'm now at about 21 centimeters. So it's a cylinder of air that I can adjust. And if you need, you can even put a little bit more water if needed. But we've got this cylinder of air. And so what we're going to do is we're going to move this up and down. Once again, this end is an open end. The other end is a fixed end because the water is there to create the reflection of our wave into our standing waves. Okay, so here's where it gets tricky. So I need one person in the group can operate that little hammer. So I've got the vibrations. I'm going to put that above my tube without them touching, and I'm going to together lift them up and down. And you'll hear right there, I hear a special noise. It sounds different there than it does there. And so I'm going to stop it there. I'm holding that against the side of my tube. My partner can now get a really good measurement, do better than my measurements. Hey, that is 12.62 centimeters or whatever that length is. Okay, so we're going to use this tuning fork, switch partners now so you each have a chance to do it, and eliminates the human error. Once again, right there's the height. Let's measure that one. After we've measured that 3 different times, now let's see if we can find a resonance. Can we take that up an octave? And what happens as the tube gets longer? Oh, there's another one right there. Okay, so now what I'm going to do is I'm now going to record that length, and that's about 22.5 centimeters for me. At 22.5 centimeters, I'm now getting a different sound, and it's a much deeper sound, and that's an indication of something's going on with the frequency of the sound, and that's due to the standing waves. And so the first one would be our fundamental frequency, and now I've got a second frequency, and is that at my F2 or F3? We're going to have to draw our diagrams and see. Okay, so once again, and then I'm going to do that 3 times again. So once again, here's my second time. There's the first one. Right there's my second one. Is there a third? Oh, there's another one. Okay, so what you're going to do is you're going to do this. You're going to do it 3 times for each frequency with this tuning fork. After you've done that and you've done your calculations, put this one back and get another tuning fork. And let's see if we can do anything different. And what does this one do? Oh, I heard it. Okay. And this tuning fork is the note of C, 261.6 hertz. You're going to do trying to find multiple frequencies, multiple resonances. I guess the frequency is not changed, but the wavelength is. And you're going to do it for multiple tuning forks. You're going to do 4 different forks. Wow, that one's nice. And that one came out of the water and made a really nice tone. But once it comes out of the water, we suddenly have switched into an open system, and it's going to change everything, and that's not what we want. So in this experiment, once again, you and your partner, maybe a group of 3, you're going to measure the diameter, you're going to record the frequency of the tuning fork. You're going to take each tuning fork, you're going to do 3 samples, get the length and measure, do it another time, and you're going to do it 3 times at one length with this tuning fork, and then see if I can get a second one with this tuning fork. See if I can get a third one with this tuning fork. Okay? And you're going to do that for 4 different tuning forks. It's kind of cool. We're making music. So just to go through what we're doing here again, you're going to make a data table with some observations. You're going to have the frequency of the tuning fork, the diameter of the cylinder, and then you're going to record the length of the first good sound that you have. But you're going to record this length 3 times. All right. Then you're going to make a separate table, and this is a results table. Results are different than data. Results is where you put your answers to the things you figured out. First thing you need to figure out is your wavelength. Second is your speed of sound. Then you're going to figure out the average speed of sound. And then from there, a percent error of the speed of sound. And you should do a Google search to find what is the accepted value of the speed of sound. Then what you're going to do is repeat the entire process with the same tuning fork, but find a second and possibly a third or maybe even a fourth different frequency, the different overtones, the different harmonics, and it's the octave levels, all kinds of words, but you're going to do that with the same tuning fork. Remember, each length you're going to record 3 different times at minimum to make sure that you've got some reliable data. So 3 times at this length, 3 times at this length, 3 times at that length, so maybe 9 times with 1 tuning fork. Then you're going to repeat this with a total of 4 different forks. So you got your first one and 3 others. Record all of this in a data table, and then you're going to put that into a results table. I'm going to show you some basic information to help you solve this. Okay, so here are 3 formulas that you are going to need, And two of them we've seen before. The first one here is just our speed of sound or our speed of wave formula. The velocity or the speed of sound is the wavelength times the frequency. We got the frequency off of the tuning fork. It was printed on the tuning fork. We need to figure out the wavelength. How do we do that? Well, here I've drawn the cylinder, and maybe I'll make this a little more obvious, right? So here was the big cylinder, and we put the green tube in it, and we had water, right? So the water here is blue inside the cylinder, and it made this bottom. So there it is, and I've got my first harmonics there drawn. I've got my first wave drawn. I've called this length x. It's not a wavelength. It's not lambda, and I didn't want to call it. I guess I could have called it L. But that length L is, we're going to add to it 0.4 times the diameter, right? So this is our diameter here. And that's going to help us figure out something. I'm calling x, and the x is about the wavelength. Is that a wavelength or is it a half wavelength? Well, that's what you need to figure out. So from here, that you can somehow figure out your wavelength using your knowledge on how waves and resonance works. Okay, so you figured out your wavelength. You put it into your speed formula. Don't forget to take your average speed. I didn't put that formula up here. It's just, add your numbers together and divide by however many there are. And then we calculate our percent error. Percent error is the absolute value of the accepted value, subtract the experimental value, divide it by the accepted value. I've even given you a possible accepted value here. Multiply your answer by 100%. You're going to put your wavelength in your results table, your velocity in your results table, your average velocity in your results table, and then your percent error for each of the 12 or so different harmonics that you found. Let's see if we can find the speed of sound.